Hello and welcome to this video in our exploration. This is video 13, part 13 of our exploration of Lagrange's theorem. So this turns out to be part 13 of that exploration. And so before, we've been thinking about this whole idea of, okay, well, we know what Lagrange's theorem is saying, but we're thinking to ourselves, well, what does Lagrange's theorem have to tell us about this whole idea that if we have a group G that's finite, whose order is p to the alpha, where alpha is some prime and where p is some prime and alpha is, well, alpha is at least 1, right? Alpha is some natural number greater than or equal to 1. So the question becomes, well, does this imply that there exists a subgroup H of G such that the order of H equals to P? Is there some subgroup, if the order of G equals to P to the alpha? Question, is there some subgroup of G that must have order P, right? That has been what has been bugging us for quite some time now. And I mean, we developed a couple of strategies. One strategy, right, one strategy we've been looking at is, well, suppose uh, let let G actually end up being an element of the group. Suppose there is some G, suppose there exists some little g in G such that order of G equals to H, right? Would this be enough for us to conclude that there exists, sorry, order of G equals to P? Would that be enough for us to conclude that there exists a subgroup of order P? And another approach we were thinking about is, well, okay, what if we perform these things using power reduction instead? Suppose that we know that we know that if the order of G is some prime power, P to the alpha, well, if we know that that means that that guarantees us some subgroup H of G such that the order of H equals to P to the theta, right? Suppose we can prove that, and here we're saying that, look, let theta be less than or equal to 1, but certainly greater than or equal to 1, but we want it to certainly be less than alpha, okay? Not less than or equal to, but less than alpha. So are we guaranteed some subgroup of G which is P of the form P to the theta, but where theta is strictly less than alpha? That is, we have a subgroup which is a prime power, again, P to something, but where the value is less than P to the alpha, right? It's strictly smaller than G, right? And we were not sure yet, but we seem to be saying that, well, this strategy of having order of H equals to P to the theta, if we can reduce the powers, and the end result is that if we start with P to the alpha, right, let's say we have G equals to P to the alpha, and we take some subgroup H, right, of order, let's say P to the theta, something less than alpha, maybe alpha minus 1, and then if this still guarantees us some other subset, let's say M, of order P to the alpha minus 2, right? If we can keep reducing powers, then perhaps it's plausible that we end up with a power, we end up with a subgroup N whose order, these are orders by the way, perhaps it's plausible that we end up with a subgroup whose order N equals to P to the, it just equals to P, right? And if any, if since all of these things are, and if we can say that N is a subgroup of G, then maybe we can conclude that order of N equals to P, right? So can you think of any other strategies? This seems to be the strategy that we're following. So let's see, is it indeed true? Right, so what we're tackling before was proving this idea, right? That, look, suppose indeed that order of G equals to P to the alpha, right? Let's suppose this is true. Why does that necessarily imply that there exists a subgroup H of G such that order of H equals to P to the theta, right? And of course, theta is being taken to be less than alpha, right? Why is this guaranteed? And that's what we're exploring before. And one of the strategies was, well, let's suppose we explore. Let's explore what happens if the consequence is not true. Let's explore what happens if there is actually no subgroup of G whose order is p to the theta. Right? What would that mean? Right? Would it mean that for every H subgroup of G, right, would it mean that for every H subgroup of G, uh, order of H has to equal to p to the alpha? Right? If we are told that, right, would this be true? Would it be true that the order of H has to equal to p to the alpha? All right? Or or maybe is there another possibility? Isn't there some subgroup that we're guaranteed to be true? What about the subgroup, the identity subgroup? Well, isn't it true that for the identity subgroup, the order of, I mean, if we're assuming that p is a prime, p is prime, and alpha is greater than 1, if we're assuming greater than or equal to 1, then can p to the alpha ever equal to 1? Right? If p to the alpha does not equal to 1, haven't we found a subgroup of G, namely the identity subgroup, such that the order of the identity subgroup is not is less than p to the alpha? Right? So, isn't this statement generally true? Well, perhaps in the case of the identity it's true, right? But sure, what about other than the identity, right? Other than the identity, right? Because the identity subgroup is, it's a nice one to think about, but the order of the identity subgroup is what? Is in the order of the identity subgroup 1. If the order of the identity subgroup is 1, how can the identity subgroup, right, have order p if p is some prime, right? So maybe the identity subgroup is not going to help us. So could we perhaps restrict what we are doing here? Suppose we restrict our work and instead said, well, okay, well, suppose that H, can we say, if this statement were not true, if the, we're trying to think about, well, what if the consequence were not true? What if we actually had some subgroup of G whose order was actually p to the theta? Okay? Well, actually, suppose that the consequence was not true. That is, there is no subgroup of G whose order is p to the theta, where theta is less than 1. And suppose we assume that we're only considering subgroups of, what? Subgroups which are not the identity subgroup, right? So can we then say the following, that for all H subgroup of G, right, what would it mean for the consequence to be true? Let's just explore what it means for this statement not to be true, that there must be a subgroup of order p to the theta. So for all H subgroup of G, let's suppose that, well, order of H, so let's suppose that H is not the identity, right? H does not equal to 1, the identity subgroup. H is not the identity subgroup. Can we at least conclude that saying that there is no subgroup of order p to the theta is that the same as saying that for all such H in G, for all H subgroup in G, H not equal to the identity, that this implies that order of H equals to p to the alpha? Okay. But if order of H equals to p to the alpha, aren't we saying that order of, and p to the alpha equals to order of G, aren't we saying that order of H equals to order of G? Okay? If order of H equals to order of G, right, what are we saying? What are the possible subgroups? Are we saying that the only possible subgroups are the identity subgroup and the group G itself? Right? Is this true? If every subgroup that is not the identity has order p to the alpha, namely the order of the group, well, aren't we saying that the only subgroups are the identity subgroup and the group itself? Right? But if this is true, suppose we pick some non-identity element. Let little g be an element of G, right? Such that little g is not the identity. Right? What is the order of G? Right? Are we saying that, would this mean that the order of G equals to p to the alpha? Okay. if the order of G equals to P to the alpha, well, aren't we saying that our group G is actually cyclic? That we can write it as G to the 0, G to the 1, G to the 2, all the way up till G to the P to the alpha minus 1. Okay. If we can say this, if our group is actually turning out to be cyclic, if we assume that no subgroup has order P to the theta, theta less than alpha, well, what can we learn from here? What can we learn about, right? So here we seem to be in the dark, so perhaps just learning as much as we can about our group may be helpful to us. Well, okay, we have a group which is, we're saying, to be cyclic now. It has elements G to the 0, G to the 1 up to G to the P to the alpha minus 1. So over here, can we find an element of order P? Right? That's the question. Well, but first question, why is it important for us to find an element of order P? Right? So let's say we're successful. Let's say there exists some H, let's say R, element of G, such that order of R equals to P. Right? Why is that useful to us? Right? If we found an element R of order P, wouldn't we be able to conclude that R to the 0, R to the 1, all the way up till R to the P minus 1 is actually a subgroup of G, and what's the order of this? Would we say that the order of this subgroup would be P? Okay, so what are we saying? Are we saying that if we can assume, if the order of G equals to P to the alpha, and there doesn't exist a subgroup of order P to the theta, then, and if that is true and we're able to conclude from there that the group is cyclic and thus has an element of order P, right? Would we be done, at least for the case where there is no subgroup of order P to the theta? Could we then, the question is, could we then divide our study into two cases, our proof into when there exists H such that order of H equals to P to the theta, and when there does not exist, when there doesn't, right? That's not how doesn't is written. When there doesn't exist H such that order of H equals to P to the theta. Suppose we're able to prove that when there doesn't exist H such that order of H equals to P to the theta, if we're able to prove that in this particular case, well, we must have a subgroup of order P. And if we're also able to prove that if there exists a H such that order of H equals to P to the theta, if in this case we're also able to find a subgroup of order P, wouldn't we be done with our problem, is the question, right? So let's see. Let's investigate. Here we're looking at the consequences of having, well, we're studying the consequences of saying that there is no subgroup, that there is no subgroup of order P to the theta, that is of some power that is less than P to the alpha. Okay. Well, and so far we seem to have arrived at this particular idea that, look, what that means is that if we get some non-identity element of the group G, it must generate the group. That is, the group G becomes cyclic if there is no H such that order of H equals to P to the theta. Okay. Well, if the group is cyclic, can we prove that the group must have an element of order P, is the question, right? So does such an R actually exist? So far we don't know. So, okay, at least let's put a question mark on this and ask the question, by examining this group G, can we find an element whose order is actually P? What about, can you think of such an element in this group whose order will actually be P? Well, maybe the first question to ask is, if we have some M, we're running out of letters. If we have some J, J is never gonna, T, if we have some T, okay. If we have some T, element of some group, how do we prove that the order of T equals to some element, let's say M? How do we prove that an element has a given order? What's the strategy for doing that? Because maybe we're not sure, but perhaps investigating this figuring out what it means to have an element of order m might enable us to guess at what element of the group will have order p. And if we can do this, perhaps we can now conclude that indeed uh, the group G actually has a subgroup of order h, provided that no h of power p to, or no non-identity h of power p to the theta exists. Okay, so let's think about this this scenario now. All right, so how do we prove that an element has a given order? That's the general question. Suppose we have some element t of some group. How do we prove that the order of t equals to m? Right? What are the possible strategies? Can you think of some? Suppose we proved that t to the m equals to the identity, okay? And what else would we need to show in order to conclude that order of t equals to m? Suppose we said that t to the m is the identity, and in fact, I mean, what is the order of a group, of an element? Isn't the order of an element the smallest natural number, such that when you raise that element to that power, you get the identity? So if we prove that t to the m equals to 1, what would it take to show that m is the smallest power, such that when we raise t to the m, such that when we raise t to it, we get 1? Suppose we proved that then for all L less than m, all natural numbers L less than m, t to the L does not equal to the identity. Suppose we prove these two things. T to the m equals to the identity, and for any power of L, for any L less than m, any natural number less than m, t to the L does not equal to the identity. Okay? Suppose we prove this. Would it be enough for us to now conclude that indeed order of t equals to m? Right? Would that be able to conclude? Would we be able to conclude that? If this strategy is valid, okay, how can we apply it to our problem? Okay, well, so what we need is some element of G, right? What form do the elements of G take? Can we say that the elements of G take the form G to the I, where I is some natural number? Okay, so what would it mean for an element of G, that is an element of the form G to the I? What would it mean for that element to have an order P? Okay, well, what does our previous strategy seem to tell us? Can we conclude the following? Can we find some G to the I in G such that G to the I equals to P? Sorry. Alright, an error. We're getting ahead of ourselves. Actually, what is the ahead for? But we're just making a mistake here. So, can we suppose we proved that G to the I, an element of G raised to the P equals to 1, okay? Suppose we found some G to the I such that G to the I to the P equals to 1, and for all L natural number less than P, G to the I to the L does not equal to the identity. Suppose we prove these two facts, fact 1 and fact 2, or statement 1 and statement 2. Right? Would that be enough to conclude that the order of G to the I equals to P? Right? So question becomes, can we find an element in this group here? Can we find some element, actually, some G to the I for which these two conditions hold? Okay. Can you think of an element in the group G such that when we raise it to the power of P, we get the identity? Right. Well, let's see. Let's suppose that G sub I to the P equals to the identity, right? Is that the same as saying that G sub I P equals to the identity? Okay. So, what do we know about elements of the group, right? So, for instance, maybe this is another consequence of Lagrange. So, this is the strategy. Let's keep it in mind. We've reached this point, but now we're wondering, well, what does I have to be so that G sub I to the P gives us the identity, right? Okay. At least can we find some I that works, and then maybe from there we might find the smallest I. Okay. So this now begs the question about which I works, right? Which I is going to work here, right? So and you know this group is a little different, right? Because well, one thing we know is that well, can this G to the I that we are looking for, can it be the identity? Right? Is the question. Can it be the identity? Right? What's the order of the identity? Is the order of the identity 1? Okay. Is 1 a prime? Alright, so whatever element we're looking for, can we say that whatever G to the I we're looking for, if we want it to have order P, then it can't be the identity. Okay. If we're saying that whatever G to the I is going to be, it can't be the identity, right? Right. Well, doesn't this mean that the order of G sub I actually equals to P to the alpha? Sorry. Right. Hmm. Are we? Alright, this is another bump in the road, it appears, in our exploration. Well, hmm. We started with some group H, so some group G. We picked some, we're looking at the subgroups of G. One of the subgroups was, well, we saw that if there is no subgroup of order P to the theta, then the only allowed subgroups are either the identity or the entire thing. Oh, okay. Right. If the only allowed subgroups are the identity or the entire thing, well, how can we ever find a subgroup of order P, right? If the only subgroups are the identity, right? If the only subgroups of G are the identity and G itself, and well, if order of G equals to P to the, if order of G equals to P to the, if alpha equals to 1, then, right, aren't we done here? Well, haven't we, isn't a group a subgroup of itself? So then haven't we already found a subgroup of order P? Okay. So suppose that the order of G equals to P to the alpha, but alpha is certainly bigger than, alpha is being taken to be bigger than 2, bigger than 1, sorry, so that the order of G is not P. Alright, if we know that these are the only two subgroups, how can we ever find a subgroup of order H, right? So question becomes, isn't our investigation here a waste of time? That is trying to find an element in the cyclic group that has order. Hmm. Yep. So this is a genuine source of confusion. Not sure how to resolve it temporarily. Let's see what we can do. Well, we just said that the only allowed subgroups are the identity and the group itself. If we assume that there is no subgroup of order P to the theta, right, right, kind of makes sense, right? Maybe we might not even have needed to do all these calculations. If there is no subgroup, right, if there is no subgroup of order P to the theta, then the only possible subgroups are the identity and itself, okay? And if that is true, well, why is that a contradiction? Right? Is there any contradiction? So notice that if we found a contradiction in this statement, if we found that actually, if we looked at subgroup of order, if we actually found that it doesn't make sense for the identity and G to be the only subgroups of the group, well then at least we'd know that the case where we can't reduce powers, that subgroups have to be proper, right? Because before we're saying like, if we have some subgroup order p to the theta, right, then from this point we had some idea about, well, maybe just keeping on reducing powers, but now we're looking at the case, what if for every h, order of h can never equals to p to the theta, right? Okay, since we're saying before that the only possible, if we look at any subgroup for all subgroups h of g, right, if h is a subgroup of g, for all subgroups h of g, right, one thing we know for sure is that h equals to, I mean, the only possible orders of h for any subgroup of g, if the order of g is p to the alpha, well, those are we seem to be saying that the only possible subgroups are the identity, or p, or p squared, or p cubed, or all the way up till p to the alpha. Right? So this is what we appeared to be saying before. And we're saying, look, suppose we eliminate the options. We say that, look, the only allowed powers, well, suppose we say that the powers that are allowed, well, we're not allowed to have the identity power, and we're not allowed to have the entire order of the group. Well, sorry, it's the other way around. All right, let's erase this. Getting ahead of ourselves here. Okay. Why are we getting ahead of anything? Right? This all ahead stuff. Okay. So, okay, let's get a dark color here. Dark is good. All right. Or p to the alpha, right there. So, at this particular point, we're saying that, look, the order of h can't be p, right? We're saying it can't be anything in between p to the 0 and p to the alpha. So it can't be p. If it can't be p and it can't be p squared and it can't be p cubed, what does that leave us with? Only the identity and p to the alpha. Those are the only possible orders. In other words, which is the same conclusion as before, that we end up with the identity subgroup and the group itself as a subgroup, right? And so, is there any reason to suppose that this can't happen? That we can't have the identity or p to the alpha as possible, that we can't have a subgroup of order whose only subgroups are the identity and p to the alpha? Is there any reason to suppose that this can happen? Right. Because suppose we're able to show that this can happen, that there's always an extra subgroup other than the identity and p to the alpha, right? Wouldn't that be the same as showing that there exists some subgroup order p to the theta? Okay. So let's see if, so this becomes our new challenge. Right. Can we show that there must be some other subgroup of H that is not just the identity and p to the alpha, supposing that alpha is greater than 1 and p is a legit prime, eh? Well, legit, there's only one, and prime legit, okay, that p is a prime. Okay, let's think about this. Hmm. So it's hard to resolve this approach, right? We're not sure if this is going to work. Um, so this pushes us to think of something new, right? Something different at least. Try a different approach. All right, let's try this approach instead. Okay. So, well, do we even need to try a different approach? Let's just say this instead. Okay. Well, since uh, okay, since since the only subgroups are the identity subgroup and the group itself, right? As we saw before, well, can't we say that then the group, at least the group itself, has to be cyclic, right? We concluded that, right? So the group is cyclic, okay? G to the p to the alpha minus 1, okay? And what can we say about cyclic groups? What do we know about cyclic groups? Right? In particular, we're looking at isomorphisms here, right? So, well, yeah, maybe you're confused. What's an isomorphism? So let's create a special kind of function, right? So let's think about what an isomorphism is. And oh, geez, did we what happened? All right. No. What did we click? Okay. Uh-huh. Okay, there's an error with the, is it with the pencil or what? I'm not sure. Okay. It was a brush size thing. All right, cool. So let's let's think about. So far we've gotten to this point, right? So we've gotten to the point where we're saying, look, the group has to be cyclic if if there are no proper subgroups other than the trivial subgroup, the identity. Okay. Well, if a group is cyclic, what else can we say about it, is the question, right? In particular, suppose we define such an operation between two groups, right? Let's say we have a group A and another group B, right? So suppose A and B are groups, okay? And suppose we defined a function phi from a group A. Well, do we want to say this in general? Do we want to say this in general? Sure. Right? This is just natural. So we are going to define an object called an isomorphism and see if it helps us here. Suppose that phi is a map or a function from A to B, right? All right? And A and B are groups, okay? And we define it as follows. That is, well, A is a group and it has some operation, right? So let's say A has the operation star and B has the operation plus, okay? All right? So suppose we define it as following. Suppose the function has the property that, well, it takes any two elements of A star, of A. So the group is not, so A is a group and the operation is star. B is a group and the operation is plus. That's what we're saying. We're not saying the group is called A star, okay? Maybe we should put it in purple to indicate that it's the operation. Wait, is that purple? All right. Let's first do some erasing here. All right. So let's put it in purple to say what the operation is. So the operation on this group is star and the operation in the group B is plus, okay? So you're wondering, well, why are we defining an isomorphism? Or why are we defining this function, right? So, and that is your challenge. Every time we develop, whenever we think about something related to this function, ask yourself, how does this relate to finding an element of order P in the group G, right? Is the question. So, sorry, I mean, we wouldn't find an element of order P, right? It's because we said that, look, if we have an element of order P, we have a subgroup of order P. But if we're looking at P to the alpha and alpha is greater than 1, that's not going to happen. So Actually, there's questions about whether this isomorphism is going to help us or not. Yeah, it appears to be time to abandon this entire approach. So remember, before we had two possibilities. One approach was to go on a reduction of powers. That is, one approach was to say, look, well, where is it again? Yeah, where do we go? Up here, okay. So one approach was to take order of G, set it to P to the alpha, and show that there exists a subgroup of one approach was to reduce the powers, find a subgroup of order P to the theta. And this is appearing to be problematic to us. At least it's not clear how to fix it. So for the moment, let's abandon this approach. Okay. And let's focus on a different one. Can we find an element of order P in the group itself? We're not going to assume that the only subgroups are the identity or the group itself. Just if suppose we're able to find an element of order P, right? Maybe that could help us. Right? So to do that, let's think of something else. So new strategy, right? Either there exists some G in the group G such that order of G equals to P to the alpha, or there doesn't, right? Or there doesn't, right? We're not sure, right? This is unknown, right? And basically our strategy now is to just find an element of order H. So these seem to be the only two cases. Would you agree with this? That either there's an element of order P to the alpha or there isn't one, alright? So let's suppose that there is no element of order P to the alpha. Okay, let's start with the first. Suppose that there is an element of order P to the alpha, right? At least what can we conclude from there? Suppose there exists little g in G such that order of G equals to P to the alpha, okay? If this is true, well, what can we conclude? Can we say that G is cyclic? That G can be written as G to the 0, G to the 1, all the way up till G to the P to the alpha minus 1, okay? Now let's think about the element. Suppose we think about the element G to the P to the alpha minus 1. Right, let's think about that element. Alright? So what is the order of that element? What is the order of G to the P to the alpha minus 1? Alpha is on the power. What's the order of that element? Okay. Alright. So in particular, can the order of G to the P to the alpha minus 1 equal to P? Right? Is that true? How would we prove that the order of G to the P to the alpha minus 1 equals to P? Right. Suppose we showed, let's first check if G to the P to the alpha minus 1 raised to the P actually equals to the identity. Is it equal to the identity? Well, what's G to the P to the alpha minus 1 raised to the P? Is that the same as G to the P to the alpha minus 1 times P? Okay. So is that the same as G to the P to the alpha? But didn't we say that G to the P to the alpha, that the order of G was P to the alpha? So if order of g is p to the alpha, doesn't that mean that g to the p to the alpha equals to 1? Alright, if that's true, then aren't we saying that g to the p to the alpha minus 1 raised to the p, which gives us g to the p to the alpha, must also equal to 1? Alright, so is this enough to show that the order of g of p to the alpha minus 1 equals to p? Is that enough for us to show this? Well, sure, sure, g to the p to the alpha minus 1 raised to the p, right? Sure, we can agree with a few statements. Okay, if g to the p to the alpha minus 1 raised to the p equals to the identity, okay, that's all well and good, but how do we know that p is the smallest power such that g to the p to the alpha minus 1 raised to it, right? How do we know? Let's put it this way. How do we know that, let's go back to the dark color. How do we know that there does not exist some n less than p, natural number n less than p, such that g to the p to the alpha minus 1 to the n gives us the identity? Because if such an n exists, can we say that the order of g to the p to the alpha minus 1 is p, right? If we can't say that, let's think about this. Can such an n exist? Can there be some n less than p such that g to the p to the alpha minus 1 times n gives us the identity? Okay, so let's think about that. What's g to the p to the alpha? I don't want to screw up the calculation here. What's g to the p to the alpha minus 1 raised to the n equal to? Is that the same as g to the p to the alpha minus 1 times n? Okay. Well, so we know what is the order of g. What did we say the order of g was again? We knew that the order of g has to equal to p to the alpha minus 1. Sorry, p to the alpha, right? So if we're going to raise, and we said that if the order of g is p to the alpha, right? Aren't we saying that p to the alpha is the smallest power to which g can be raised to give us the identity? If that's the case, how can something smaller than p, how can there exist some n less than p such that p to the alpha minus 1 times n actually gives us p to the alpha, right? Because if we're looking for the smallest thing that makes this expression the identity, aren't we saying that we're looking for the smallest n such that p to the alpha minus n minus 1 times n gives us p to the alpha, all right? But how many n exists such that p to the alpha minus 1 times n equals to p to the alpha, right? Isn't there just one n that does that? So can we say that then n has to be p to the alpha from this equation times p to the minus alpha plus 1? But what does that give us? Doesn't that just give us p? So, okay, given this information, can we conclude that at least the order of g to the p to the alpha minus 1 has to equal to p? Okay. So if we found, so here we looked at the case where they actually exist an element of order p to the alpha minus 1, okay? So that's the case we're able to look at. There exists an element of order p to the alpha minus 1. So we're saying, are we saying at least that if there exists a g, element of g, such that order of little g equals to p to the alpha minus 1, right? Sorry. If there exists an element of g such that order of g equals to p to the alpha, then we can conclude that there exists some, let's say g2, right, element of g such that order of g2, okay, such that order of g2 equals to p, right? here maybe we're setting g2 equals to g to the p to the alpha minus 1. Okay. If this is true, then isn't g2 to the 0, g2 to the 1, all the way up till g2 to the p minus 1 a subgroup of G that has order H? Alright? So are we saying that at least, maybe we haven't done it for all the cases, but can we at least conclude the following, that indeed if H is a subgroup, sorry, if order of H, do you agree with this theorem? If the order of G equals to P to the alpha, right, and there exists some little g element of G such that order of G equals to P to the alpha, then there exists a subgroup of G such that a subgroup H of G such that order of H equals to P, right? Would you at least agree with this statement, that provided we have an element of order P to the alpha? So if we can't prove the whole case, at least maybe we can prove a special case. If we have an element of order P to the alpha, are we at least guaranteed that there must be a subgroup of order P? Right, so see if you're now convinced that this statement is true, and maybe you could add another statement. Further, okay, we kind of guessed that the subgroup is cyclic, but if there exists a subgroup of order P, can we at least say that the subgroup is also cyclic? Okay. But what question does this raise? Okay, so if we've shown that indeed, suppose there's an element of order, some element of the group whose order is, if indeed supposing that there's an element of order P to the alpha, helps us to conclude that we have a subgroup of order P, well, natural question is what? What if we have a group of order P to the alpha, but what if order of G is not P to the alpha? Right? For any alpha, for any G in G, right? What if there is no element of order P to the alpha? Can we conclude that there must exist a subgroup H of G such that order of H still equals to P? Right? So now this is the special case we are left to look at. Well, what happens when there is no element of order P to the alpha? What do we do then? Well, thank you very much for watching this video, and have a relentless week. Bye.